In the last video we looked at the Heaviside or unit step function, and we saw that the limit as t tends towards 0 of this function does not exist. The reason it does not exist is because if we approach 0 from one side, we get one answer, we get 0. And if we approach 0 from the right hand side, let t tend towards 0 from the right, then the function approaches 1. So we get two different answers depending on which side we approach 0 from. Now we want the same answer for this limit to exist. However, we can consider one-sided limits. We can consider the limit as t tends towards 0 from the left, indicated by putting a minus sign next to the 0. And if we do that, the answer is actually 0. It's pretty clear from the graph that as t approaches 0 from the left, then the graph itself approaches 0. Actually, the value of the function at 0, in other words h of 0, is not equal to 0, but it's equal to 1, as we saw in the previous video. But the idea is that h of t is approaching 0 as t approaches 0 from the left, but t is never equal to 0. If t was equal to 0, then we would have h of 0 equals 1. Then we'd have this jump. We're not dealing with that though. We're just, t is approaching 0 from the left but never reaches 0. So h of t is approaching 0 but never reaches 0. At 0 we have the jump. h of 0 is equal to 1. Similarly, we can talk of the limit as t approaches 0 from the right of h of t. We indicate that by putting a plus sign next to 0. So we are approaching 0 from the right hand side, and as you can see, h of t appears to be approaching 1, and indeed it is. So the important point is that if the limit as t tends towards a of any function f of t is L, then the left-sided limit and the right-hand-sided limit give the same result, L. So the limit as t tends towards a from the left of f of t will equal the limit as t tends towards a from the right. And the result will be the same as here. Now we can also turn this statement around. If the two one-sided limits exist and are the same, in this case equal to L, then the limit as t tends towards a of f of t is L. Let's look at this example here that we saw in a previous video. G of x is x squared plus 4x minus 12 over x squared minus 2x when x is not equal to 2. But when x is equal to 2, g of x is 6. So at x equals 2, g of x is 6. We saw that if we plugged 2 into this expression here, we get 0 divided by 0, which is indeterminate. That can be anything we like. So we have a gap in the curve here. This point has been removed from the curve. Anyway, let's consider this one-sided limit. X approaches 2 from the right. Well, you can see that g of x is approaching 4. It's certainly not approaching 6. Now let's consider the limit as x approaches 2 from the left of g of x. So now we're going towards 2 but from the left. We can see that g of x is approaching 4 from above, or from the right if you like. So this limit is also 4. Since both of these values are the same, we can say that the limit as x tends towards 2 of g of x is 4. Here we have a graph of the function f of x. Now this is a true function. For each value of x there is a unique value of the function. So for example, if x is minus 1, we have just one value. So we draw a vertical line through minus 1 and it cuts the graph at just one point. Let's consider f of 1. Well, if we draw a vertical line through 1, it actually only cuts the graph at one point. This point has been removed from the curve, but this point is included, the solid point here. So again, we just get one value. So if we take any vertical line and you'll see that it cuts the graph at just one point. Similarly at 6, this point has been removed, So this vertical line at the line x equals 6 cuts the graph at one point, namely the point 6, 2. Notice that f of minus 4 does not exist. That point has been removed from the curve. Let's consider the limit as x tends towards 4 from the left of f of x. Well, I want to make this minus 4. X approaches minus 4 from the left. So you imagine moving towards minus 4 but never reaching minus 4. What's happening to all the values on the graph? Well, we could pick points along here that are less than minus 4 but approaching minus 4. Go up to the graph and go across. We can see that all these values appear to be approaching 2, and indeed they are. So this limit is actually equal to 2, even though the function is not defined at minus 4. F of minus 4 does not exist. Now, we can also see that if we approach minus 4 from the right, written like this, limit as x tends towards minus 4 with a plus sign, that our function is approaching 2. So if we pick any values that are greater than minus 4, go up to the graph and go across, we can see that as these values approach minus 4, as x approaches minus 4 from the right, then f of x is approaching 2 from above. So since we get the same value for both of these one-sided limits, we can conclude that the limit as x tends towards minus 4 of f of x is 2. Now, as we saw earlier, notice that f of 1 is equal to 4. The point 1 minus 2 has been removed. We can't have a function having more than one value at a given value of x. So at x equals 1, we can't have the function equal to 4 and minus 2 at the same time. Functions must have a unique value for each value of x. Let's look at the limit as x tends towards 1 from the left of f of x. So we are moving towards 1 from the left, but never reaching 1. What's the story with f of x? Well, if we go up to the graph, there's nothing below these points here, so we have to go up to the graph and across. We can see what's happening actually. As x approaches 1, f of x appears to be approaching 4. Again, x is not equal to 1 while we're taking this limit, and f of x never reaches 4, but it's approaching 4. We can make f of x as close as we like to 4 by taking x as close as we like to 1, but from the left. Now let's approach x. Let x approach 1 from the right. So what's happening to f of x? Well, there are no points above this part, these values of x. We have to go down and across. So as x gets closer and closer to 1 but from the right, it appears that f of x is approaching minus 2 from below. So as we take values along here that are getting closer and closer to 1 but never reaching 1, we can see that the values of the function are getting closer and closer to minus 2 but never reaching minus 2. Since both of these limits give different results, we say that the limit as x tends towards 1 of f of x does not exist. In this graph, f of 6 is equal to 2. The point 6, 5 has been removed from the curve. So again, we want our function to be a genuine function, that is a single valued function. So we just have a single value for x equals 6. That single value is 2. Let's consider the limit as x approaches 6 from the left of f of x. So we're approaching 6 from the left but never reaching 6. So what's the story here? Well, if we consider these values that are around here, well, f of those values are values over here. And as we're getting closer and closer to 6, we can see what's happening. F of x appears to be getting closer and closer to 5. But we never reach 5. So this limit is equal to 5. Now let's take the limit as x approaches 6 from the right of f of x. So let's see what's happening. Let's take this value here and go up to the graph. And if we go across, we get a value that's greater than 5. And you see as we move closer and closer to 6, if we go up to the graph and across, we get a value that's greater than 5. So what's happening here is that we are approaching 5 as x approaches 6 from the right. We're actually approaching 5 from the right, or approaching 5 from above. So, since both of these values are the same, both one-sided limits are the same, we can say that the limit as x tends towards 6 is 5. So this limit exists and is equal to 5.